again at the University of Colorado at Boulder. And so Amy is going to be talking to us today about mechanisms of flash flood generation in a gullied high plains grassland, evidence for partial contributing area runoff.
All right, thank you, Aisha. So I'm Amy. I worked on a continuation of my last summer project with Greg Tucker on flash flooding in semi-arid regions. So when a flash flood, or actually when a storm occurs, there's always a chance for a flash flood to emerge. In this presentation, I'm going to outline a study in which we set to determine these contributing factors for a flash flood to occur. Before I reveal these contributing factors to you, I am going to go over a little bit of vernacular I'll be using throughout this talk. This is supposed to denote the beginning of a storm. You have these ominous storm clouds, and then maybe some lightning, and then you start to get rainfall. And this rainfall hits the soil surface, and there's only a certain amount of capacity that this soil can hold the water, which is its infiltration capacity. Once it cannot hold any more stormwater, the rainfall becomes runoff, and if the runoff is enough, it can be a flash flood. Flash floods can also appear in other mechanisms as well. Periods of dryness tend to form this semi-impermeable seal on top of the soil surface, which makes rainwater basically bounce off and become runoff, and there's less infiltration during these events. We focused on surface flow primarily, left out the equation of groundwater flow in our interpretations. So just focusing on infiltration excess when the rainfall rate exceeds the infiltration rate of the soil, and then the saturation excess when the soil cannot hold any more rainfall and it's at its infiltration capacity. If floods can be defined as water rising in response to a storm in a normally dry environment. A flash flood can be associated with a flood that's rising very quickly in response to a storm. They're very dangerous because they occur with very little warning, and our main focus was them being the main driver in erosion in semi-arid regions. This is an example of the devastation that occurred from the Boulder flood in Longmont. That's Sunset Bridge. I'm sure a lot of you guys were affected by that particular devastation. So that's a portion that we should look into because it's something we should care about for our infrastructure stability in a society. And as I mentioned, it's a main driver in erosion in semi-arid regions, and this erosion occurs in the form of gullying. And gullying produces these large sediment loads that infiltrate into surface water supply, which can contaminate water supply for our consumption. The news gets even worse when agricultural land is eroded and these fertilizers and chemicals are getting into our water supply. And then as shown in the first picture and this next picture in Jamestown, sorry, I'm trying to use that to point, we have infrastructure failure where previously stable surface is eroded by these flash floods and hence failure occurs. Unfortunately, there is little known about rainfall inputs and flash flood generation, so we need a general reference for flash flooding. My big question throughout the duration of this study was, what are the contributing conditions necessary for a flash flood to emerge? My hypothesis was pretty intuitive. I thought rainfall intensity and duration, coupled with antecedent soil moisture, more as a secondary control on flash flooding. And we chose to study at West Bijou Creek, which is a prime example of a dryland area impacted by gully erosion. It's located in the Denver Basin in east central Colorado, right here in this blue circle, about 40 minutes east of Denver. And the reason why it is so susceptible to erosion is because of its composition, which is poorly lithified sandstones, mudstones, and lignites. In this area, we use two measuring techniques. The first is denoted by our study site. which is a short-term study on the infiltration rates of vegetated land versus bare patches of land. And then we had a data collection site, which is a long-term 6-year study that measured storm occurrence, and through these storm occurrences, we were able to determine whether a flash flood occurred or not. So it's great to have storms to track. So what we did is each storm, we plotted this intensity curve, or intensity throughout these durations. And I'm getting ahead of myself. Let me explain the sonic ranging sensor really fast. I have too many things going on right now. This is a sonic ranging sensor. It sends kind of a pulse down to the ground. It's set up, you can't really see it in this picture, but it's over here. This mechanism is about 1 meter above the land, and it sends pulses that determine the water surface heights during a storm. And it's triggered by this tipping bucket rain gauge right here that measures rainfall every 1/100th of a centimeter, and communicates with the sonic ranging sensor to start taking flood stage height. And with this data, we were able to produce these flash flood hydrographs. Flash floods are really easy to pick out in these storms because they have really defining characteristics. The first is that they have a sharp increase. This is water surface height on the y-axis, and they have a very sharp increase in water surface height in regards to duration of the storm. And then once they reach their peak, they gradually recede back to 0 in water surface height. So I mentioned before that we wanted to focus on the rainfall intensity during these storms, like why were some storms producing flash floods while others weren't. And so we took these storms and we averaged their peak intensity through 15 minutes and derived this graph where we plotted flash flood occurrence as these blue triangles and no flash flood occurrence with these red triangles. And using a linear discriminant analysis, we were able to kind of create a threshold between flash flood occurrence and non-flash flood occurrence. And this intercept tells us the minimum intensity required to produce a flash flood instantaneously, which is approximately 32 millimeters an hour. So pretty significant rainfall needed to produce a flash flood quickly. And then we took this a step further and doubled our sampling interval to 30 minutes an hour to sample a wider range of peak intensity, and got this graph, which has a similar threshold line to the one seen in the 15-minute intensity. You need at least 20 millimeters an hour of peak intensity to produce a flash flood. And we were pretty pleased with the similar results between the two experiments. And some conclusions we can derive from this long-term 6-year study is that immediate flash flood generation occurs at 15-minute peak intensities of over 32 millimeters an hour, and at 30-minute peak intensities of over 20 millimeters an hour. And then I mentioned the semi-impermeable seal in the beginning in my animation, and this is just to reiterate that storms that follow periods of dryness are more likely to produce flash floods due to these dry antecedent soil conditions in the surface. So it's great finding these storms and identifying flash floods versus non-flash floods, but we're missing a huge chunk, which possibly is a huge control on this runoff generation, and that is infiltration rates. So this is a picture of West Bijou Creek on a typical summer day. You can see there's a wide range of vegetation throughout the basin. You have these green valley floors and then dispersed vegetation, and then you have these bare slopes. There's no pattern between the dispersion, which makes this basin a little difficult to study for flash flood generation. So to try and remedy this situation, we conducted these short-term sprinkler experiments to measure these infiltration rates between vegetated and bare plots. These are the examples. We had 2 plots, one on bare, which was about 0.6 square meters in area, so not incredibly big, but sufficient. And this is our vegetated plot. It's the same shape as the bare plot. They have the same slope, and so we know our application rate with these sprinklers, and we changed the sprinkler. We changed up the amount of sprinklers to change up the input rate just for, I'll get into that, but we did use multiple sprinklers for multiple tests. And what didn't infiltrate into these areas was funneled into these tubes and effectively into this bucket. And this bucket had a scale that laid underneath of it, and we took pictures of this scale to timestamp these the volume and the timing of this runoff. And it was great because we were able to generate this rainfall data without relying on rainfall, and we kind of improvised a lot, but effectively able to produce a cumulative runoff rate, which is denoted in this next slide with these two graphs that we created. These horizontal portions in this graph they don't mean anything. It just means we weren't applying any sprinkling rate because we were dealing with technical difficulties. But overall, the important thing to take away from these are the slopes. And the slope is the runoff rate of each plot. So unfortunately, these are just for bare plots because our vegetation plot had a higher infiltration rate than our max sprinkling rate. So we determined that number to be about 53 millimeters an hour for 3 sprinklers. The sprinklers were supposed to spray about 23 millimeters an hour, but one failed and produced less than half of its rainfall rate it was supposed to. So that's one thing we would like to nail is the exact vegetation infiltration rate. Our bare plot basically shows that it has a very low infiltration rate, and vegetated shows that there has a very high vegetation rate. Even though the numbers are pretty different depending on the experiment, we determined that the vegetated plot from last summer that we set up mainly had brown vegetation, kind of dying, dead plants. And then this summer, we had just this greenery garden in our vegetation. So it's saying something about the input, and maybe the root systems are becoming more extensive, which has an effect on the vegetated infiltration rate. And we just wanted to show that stark contrast between the two plots, just based on vegetation or non-vegetation. A couple conclusions we can make from both our short-term and long-term study that rainstorms with a 15-minute peak intensity above 32 millimeters an hour or 30-minute peak intensity above 20 millimeters an hour produce flash floods. Storms with heavy rainfall that follow periods of no rainfall, so dry periods, are most likely to produce flash floods. And our sprinkler experiment revealed bare areas are more likely to produce flash floods because of their low infiltration capacities. And we can take these conclusions and apply them to a few implications of gully erosion. The first is that the incision occurs mainly during summer months. So we're talking monsoonal season, monsoonal climates where you have lots of bursts of this intense rainfall that erodes these gullies. And this is an example of a head cut of a gully. You see there's this kind of clump that's about to fail because this water is running off, and since there's no infiltration rate in the bare land, it's basically pushing this clump off of the wall, and which is a huge sediment load, which can infiltrate into the water supply. During this incision, there's also the idea of the self-enhancing feedback, where bare slopes are more likely to conduct this runoff, and this runoff incisors more and more bare land, which feeds the self-enhancing feedback. I'd like to thank Greg Tucker for taking me under his wing again for the second year, the Plains Conservation Center where all of our experiments took place, the RESESS program, and all of Greg's grad students were amazing help, and Kaylee, our RESESS grad student. And thank you very much. I don't think I have a slide after that. Uh-oh.
All right, thanks, Amy. We ran out of batteries in the other microphone. So does anyone where are you going? Yes. Does anyone have any questions? All right, Jenny. I'll just run this back and forth.
So I actually have 2 questions. The first one is why this particular study area in Big Thompson? Like, is there something important about flash flooding in that location that people are worried about, or why is the study location important?
Well, Greg has had a long partnership with the Plains Conservation Center to allow these experiments to take place. So he has a lot of data from his past grad students that I was able to kind of piggyback off of. It's also composed of these really erodible surfaces and sediment that is susceptible to this flash flood erosion. So it does have to do with the composition, but it's mainly that we have a good relationship with the Plains Conservation Center, which is a semi-arid grassland, just happens to be. And then there's just this lack of study in semi-arid regions on flash flooding as opposed to humid regions where flash flood input is relatively well understood.
Okay, and kind of going along with that, like I was looking at your picture of the vegetation, and I was thinking, where I grew up, there's a lot less vegetation, but it's really susceptible to flash flooding, like parts of Arizona, like northeastern Arizona, like Canyonlands. So how would you adapt your study to look at gully erosion in those areas?
We definitely have to do more experiments focusing on the bare area. We'd probably take into effect antecedent moisture conditions, maybe sediment composition. Vegetation has shown a huge role in runoff interception. So there wouldn't be as much interception, obviously, in that area that you're describing with primarily bare land. So we would definitely have to modify it to focus more on the actual sediment, maybe, and the characteristics of that, rather than the vegetation, which was a huge ecological part in this geomorph study. So.
Okay, thanks. Good job.
Thanks.
Any other questions, Joe?
Yeah, I was wondering if you had spent any time looking at various slope angles, the topography, and how that impacted the uptake of the water infiltration.
We didn't, for our sprinkler experiment, we did measure the slope of the topography, and they did have matching, pretty similar within a couple degrees of similarity. I can't recall the exact number off the top of my head, but the slope of topography has not been as big of an influence in our study as it could be.
And Christine?
Okay, in your plot of rainfall rate versus storm duration, I was just wondering, do you or have you made any plans, or how would you go about tagging the data points as to whether they were in drier conditions versus wet, or the bare earth versus vegetation? Do you think that would affect your results?
We were able to track periods of dryness because these instruments, the sonic ranging sensor and the tipping bucket rain gauge, had these time stamps, so we could see, the end of one storm and the beginning of the next. We would just kind of determine the gap, like, was it a couple days, was it a couple hours, was it a whole week? It was more preliminary analysis in that respect. That is definitely something that needs to be taken into consideration for further study. But overall, I think it's important to just focus on the role of vegetation and how different the infiltration rates are and how it plays into runoff interception for flash flooding.
Just a quick follow-up. Have you looked at PBO H2O and their soil moisture measurements, and do you think that would help?
Yeah, I definitely do. I've been introduced to their toolbox. I did not put it in this summer's, but we will be continuing research into the fall, and that is definitely something I want to look at. So I feel like that's more accurate results that can play into our implications and conclusions. So.
Celia?
So you mentioned that there were some results in less arid areas. How did your results compare to similar things in other regions?
Because
Like, were
this
you
is,
surprised, or was it very different?
it wasn't really different. Again, it was the main control of vegetation in both areas. Because humid regions have more water content, their antecedent moisture condition. I don't know if it's more important or less important, just depending, because the plots we took, or the core samples we took of antecedent conditions they ranged from about 15 to 30% in volumetric water content. And I want to say it's kind of up to your interpretation if that's saturated or dry, just depending. It's normally the volumetric content cannot be over 50. So I think I haven't really looked much into the humid study. I just know that the input generation, but I think that would be a great thing to write into and present on, is the difference between humid and semi, and if there can be, if the data overlaps or if it's completely separate.
Anybody? Oh, David.
So this is probably a very simple question, I apologize, but in this area, why is the infiltration capacity so much greater for vegetation versus bare?
There have been a couple different studies. It's not just in this region. It's in all semi-arid regions where these vegetation growth has its own self-enhancing feedback, where it starts off as a patch of vegetation and it intercepts this runoff, and it's able to store this runoff as run-on into the plants and fueling their growth. So the more runoff it can intercept, the bigger it can grow, and it's a self-enhancing feedback with water input and growth of vegetation. So yeah, you generally see huge patches where there's tons of runoff. So they're watering the plants.
Of the roots? Sorry. Does the depth of the roots affect that at all, or?
It probably definitely does. That is also something we have not quite analyzed yet, but I definitely think the root system has a lot to do with curving pathways in the soil. Thanks.
Fran. One for everybody. I love it.
This is the same question I asked Diana. So you mentioned that you were going to continue the research. So are you starting grad school, or?
No, I'm not starting grad school this fall. Taking a year off, maybe get some work experience. But I do want to continue this because I think our findings are really important, and it ties a lot of loose ends together in the literature. Couple things, we want to do some numerical modeling in the basin, have like a hybrid model with, random vegetation and bare plots, and how the flood would run through the basin, just simulate different events and different variables, I guess, bare versus vegetated, primarily using these the vegetation infiltration rate and bare infiltration rates that we get from this study, to incorporate into a numerical model, and maybe do some work on the sediment.
All right. Thanks, Amy.
Thanks.